Welcome to the deep dive. Today, we are really pushing past just, the scaling laws of artificial intelligence. We're getting right into the architectural trenches.
Yeah, deep dive is right.
We're tackling one of the biggest, paradoxes facing modern AI research, the massive size of current large language models versus, frankly, their inability to perform some basic, deliberate, algorithmic reasoning.
It really is the elephant in the room, isn't
Yeah.
it? And it's frustrating. I mean, especially for researchers who are looking for robust, verifiable logic, not just fluency.
Right.
We got models with billions, even trillions of parameters, but their fundamental architecture, these fixed depth transformers, they just limit the true computational depth. They're amazing statistical pattern matchers, no doubt.
Absolutely.
But they are still fundamentally constrained when it comes to certain kinds of thinking.
And constrained. That means they belong to these low complexity classes, right? We hear terms like ACO1 and TC dollars thrown around. For our listeners deep in the field, this isn't just alphabet soup. It defines a real hard limit.
Exactly. When a transformer has a fixed depth, its computation is, well, it's basically confined to constant depth circuits. AC dollar models, for example, they struggle with tasks like parity. Is the number of ones even or odd? Or majority vote over a sequence? Simple stuff, algorithmically.
Stuff that requires looking across the whole input.
Precisely. Now, modern transformers, technically, they might fall into TC dollars because of things like attention, which allows some parallel computation. But they still struggle with tasks needing long serial dependencies. Step-by-step logic like counting, or planning many steps ahead, or searching through possibilities. They just can't robustly simulate that. Their effective computational path is, well, shallow.
And the go-to solution, or maybe the band-aid, has been chain of thought prompting, SANT. You basically force the model to talk itself through the steps.
Yeah, externalizing the reasoning.
Right.
And Conti is, frankly, a brittle clutch. It makes the model generate these huge, slow sequences of tokens. Inference becomes incredibly slow, especially for hard problems.
And it breaks easily.
Oh, definitely. Super sensitive to how you phrase the prompt. And if the reasoning chain is long, one little mistake and the whole calculation just collapses. Plus, and this is crucial from the sources we're looking at, it's data hungry. It often needs special examples broken down by humans.
So it's faking it till it makes it, almost. Leveraging fluency to mimic reasoning, not actually doing it structurally.
That's a good way to put it.
So if the architecture is the real bottleneck, the solution has to be architectural too. And this leads us somewhere completely different, doesn't it? This idea of latent reasoning.
Yes, where the deep computation happens inside the hidden state space efficiently over time, not simulated externally.
Okay, so that's the core idea we're digging into today.
That's the breakthrough. We're looking at models that use recursion to embed computation over time. They achieve really deep algorithmic reasoning, but with tiny parameter counts.
And the two main players here.
We're dissecting the Hierarchical Reasoning Model, the HRM, which kind of kicked this off at, 27 million parameters? Modest, right?
Tiny by today's standards.
And then its successor, which is even more astonishing, the Tiny Recursive Model, TRM. This thing gets state-of-the-art results with as few as 7 million parameters.
7 million, okay. So this deep dive, it's going to get technical. It's really for you, the AI researcher listening, who's looking for structural answers beyond just throwing more parameters at the problem.
Absolutely.
Our mission today: compare these recursive architectures, understand the clever mathematical tricks they use, and really explain how these tiny models are just systematically outperforming giants models 10,000 times bigger on benchmarks designed to test real algorithmic thinking.
And just to set the stage, here's that shock factor number. The TRM, 7 million parameters, hits nearly 45% accuracy on the ARC-AGI-1 benchmark.
Wow, and how does that compare?
Well, compare that to something like Deepseek R1, 671 billion parameters, which scores about 15.8% on the exact same task.
Okay, that's not just an efficiency difference. That's pointing to something fundamentally different, maybe even wrong, with the pure scaling approach for this kind of reasoning.
It suggests a structural failure, yeah. Maybe the future isn't just static width, but efficient temporal organization. How computation unfolds over time.
Okay, let's start with the first step, the precursor. The Hierarchical Reasoning Model, HRM. You mentioned its conceptual foundation comes from neuroscience.
That's right. That's where the initial inspiration came from. The researchers looked at the brain and tried to pull out 3 key principles for organizing complex thought.
What were they?
First, hierarchical processing. The brain doesn't do everything all at once, right?
Yeah.
You have higher level areas doing abstract strategy, planning, setting goals.
The big picture thinking.
Exactly. And then the lower level circuits handle the fast, detailed execution, the crunching of the numbers, so to speak.
This sounds a bit like the System 1, System 2 idea from cognitive science. Slow, deliberate thought, guiding fast, intuitive processing.
Precisely the analogy. And that leads straight into the second principle, temporal separation. These high and low levels need to operate on different timescales. Think about brain waves. You have slow theta waves, maybe setting context, dealing with memory cycles, and they modulate the faster gamma waves doing the rapid local computations.
Yep.
HRM tries to map its recurrent loops onto these separate coupled timescales.
Interesting. And the third principle, you mentioned it touches on the gradient problem.
Recurrent connectivity. This is key. Recurrence lets the model iterate, refine its thoughts, revisit its state multiple times.
Without needing a super deep network physically.
Right. And crucially, without the massive memory costs you get with standard backpropagation through time, BPTT, when you unroll a very deep sequence. The goal was computational depth without that crippling memory trace.
Okay, so principles established. Let's get into the nuts and bolts, the architecture itself. You called it the dial model. Tell us about the components.
Sure. The HRM has four main learnable parts. First, an input network, $5, takes the raw input $6, embeds it into the hidden state space. Pretty standard.
Right.
Then the two core recurrent modules, a low-level module and a high-level module, 5HH here. These are the workhorses doing the iterative computation.
Okay.
And finally, an output network, $5, that takes the final state and decodes it into the prediction.
And 5 they aren't just simple RN cells, are they? They're more modern.
Correct. They're actually built using identical encoder-only transformer blocks, specifically 4-layer networks each. And they pack in the usual modern LLM tricks, rotary positional encoding, ROPE, gated linear units, specifically switch LU and RMS norm.
RMS norm after the residual connection. The post-norm setup.
Yes, post-norm.
Yeah.
Which turns out to be important for stability later on.
Yeah.
And another key detail, no bias terms in these transformer blocks. That simplifies some of the fixed point analysis they were trying to do.
Got it. Now the dynamics, how does this nested cycle thing work? That's where the depth comes from, right?
Absolutely. The whole computation unfolds over otter-dollar high-level cycles. And within each high-level cycle, there are $2 low-level time steps. So the total effective depth isn't just 4 layers, it's never times dollar.
Okay.
The core recurrence happens at the low level.
Right.
The low-level state, let's call it ZLI, updates at every single time step.
Constantly churning.
Yeah. The update rule looks something like this mathematically. ZLI1, ZLI1, DHI1 tilde.
Okay, let's break that down. It depends on its previous state, ZLI1, the input tildes.
And crucially, the current high-level state, ZLI1. Notice the subscript there.
So ZLLers is the fast engine, but its behavior is steered by the slower-moving siler, like a governor.
Perfect analogy. ZLI dollar stays fixed for all low-level steps within a cycle. It only gets a chance to update after the LiDA module finishes its dollar steps.
And how does Xi update?
It takes the final low-level state from that cycle, ZLI teller, and uses that to compute its new state via the CLI network. It's like an abstraction or a summary step based on the detailed computation done by teller.
Okay, so this periodic hierarchical update, that's how it tackles the problem standard deep RNNs face premature convergence.
Exactly. If you just stack recurrent layers very deep in a standard RNN, the updates often shrink towards zero really quickly. The forward residual, the change in state vanishes.
The network basically stops thinking. It gets stuck.
Gets stuck in a fixed point too early. Computation just stalls. HRM avoids this with what they call hierarchical convergence. The LALA module does converge towards an equilibrium point, so but because ZL's calculation depends on Cele-Oshie, it's only a local equilibrium, specific to the current high-level context provided by CLL.
Okay.
Then when the ISHAR module finally updates using ZLA, it changes the high-level state. This shift effectively kicks the LALA module out of its local equilibrium and forces it to start searching again towards a new local equilibrium defined by the new ZL.
So ZLX acts like a reset button or maybe redirects the computation. It keeps the forward residual high, keeps the network actively computing over many, many cycles.
Precisely. It enables that enhanced effective depth they mentioned, up to 384 layers worth of computation in some settings, without physically stacking hundreds of layers. It's depth achieved through time, managed by this hierarchical restarting.
Very clever. But getting that depth is one thing. Creating it efficiently is another. This brings us to that IFT approximation you mentioned earlier, the mathematical trick.
Yeah, the trick to avoid the memory cost of backpropagation through time, BPTTT. This gets a bit technical, but it's crucial for understanding HRM's design and also its flaws.
Let's dive in. BPTT's problem is memory, right? OT dollar costs.
Exactly. To get the true gradient, BPTT needs to store the activations for every single state transition across the entire unrolled sequence of 2 steps. If T is large, that memory usage becomes prohibitive.
So HRM needed an O-Dunner memory solution. Constant memory regardless of depth.
Right. They borrowed ideas from deep equilibrium models, or DEQ. The theoretical underpinning is the implicit function theorem, IFT. The IFT says basically if your recurrent network converges to a stable fixed point, you can calculate the exact gradient without unrolling the whole sequence.
Oh.
It involves the Jacobian of the residual function at the fixed point. Specifically, you need its inverse, 1JF1
Okay, but calculating and inverting a Jacobian for a big neural network, that sounds computationally nightmarish.
Totally impractical.
Yeah.
Absolutely prohibitive. So HRM made a huge approximation, the one-step gradient approximation. They just assumed that this inverse Jacobian term could be approximated by the identity matrix 1
And so I and JF1 approx 1, that seems bold.
It's a very strong assumption. What it means practically is that when backpropagating the error, you only trace it through the very last state transition. You ignore the entire history of the recurrence leading up to that point.
Wow. Okay, so the gradient path gets massively simplified from the output head back to the final SAM, back to the final sans, and then back to the input embedding. And that's it.
That's it. And the payoff is that owner memory footprint. Training costs decoupled from the computational depth $2. A huge win for efficiency.
If the approximation holds.
If the assumption of convergence holds. And as we'll see, that if turned out to be a very big if. It was HRM's Achilles heel.
Okay, before we get to the critique and the TRM revolution, we need to cover the other training techniques used in HRM, deep supervision and ACT.
Right. Deep supervision was used mainly for regularization and providing more frequent learning signals. Instead of one long forward pass, they'd run multiple shorter forward passes, let's say 70 segments, on the same data sample, XS.
And the key trick?
The hidden state, segment $, at the end of segment $, is detached from the computation graph before being fed as the initial state for the next segment plus segment by.
Detached, meaning gradients don't flow back across segment boundaries?
Exactly. It breaks the long credit assignment chain, preventing gradients from vanishing or exploding over really long computations, but it still lets the model learn from intermediate results within each segment. It's like having mini supervision points along the way.
Makes sense. Turning one long problem into several shorter ones. And the other technique, ACT, adaptive computational time.
Yeah, ACT. This is directly inspired by that System 1, System 2 idea, managing computational resources. The goal is for the model to dynamically decide when it has computed enough and should halt.
How did HRM implement that?
They used a Q-learning approach. A small Q-head network was attached to the main model. This head predicts the Q values for 2 actions, halt or continue.
Okay, reinforcement learning territory.
A little bit. The loss function then combined the main task loss, like cross-entropy for the prediction head, with a second term, a binary cross-entropy loss on the Q values. This second loss nudged the network to predict halt when its prediction was actually correct, using a target signal.
So the total loss looked like LLACT pulling Fecho plus text binary cross-entropy carry.
That's the one.
Now, Q-learning, especially for deep sequential stuff, can be really unstable, prone to divergence. How did they keep it stable enough for ACT to work without things like complex experience replay buffers?
That's a really important technical point. They achieved stability through specific architectural choices that helped keep the parameters bounded. 2 things were key. Using that post-norm architecture, RMS norm after the residual connection.
Which we mentioned earlier.
Right. And using the AtomW optimizer. AtomW includes weight decay, which helps prevent the model's parameters from exploding in magnitude. There's theoretical work suggesting that for deep networks, keeping parameters bounded is crucial for stabilizing learning dynamics, especially in RL-like settings.
So they stabilized it structurally through the architecture and optimizer rather than adding complex algorithmic machinery like replay buffers.
Exactly, which kept the implementation relatively clean even with the Q-learning component.
Okay, so HRM. 27 million parameters, proof of concept, recursion works, beats COT on some tasks. But, as you hinted, it had problems. It wasn't the final answer.
Not by a long shot. It was effective, yes, hit 55% on Sudoku, which was impressive then. But researchers quickly saw it was, well, overly complex and built on some shaky assumptions.
What were the main points of failure that led to the TRM, the Tiny Recursive Model?
3 big things, really. First, that IFT concern we discussed. The math just didn't hold up in practice.
The one-step gradient approximation.
Yeah. The whole justification relies on the network actually converging to a stable fixed point before the gradient step happens. But when they looked empirically, especially for the harder tasks using the configuration they reported, T2 add E2 and T2, the forward residuals for both dual decimals and zeros were still way above zero.
Hey, hang on. So the system was still actively churning, still thinking, when they applied the gradient calculation that assumed it had stopped thinking.
Precisely. It hadn't reached the required equilibrium. So the one-step gradient wasn't just an approximation, it was fundamentally inaccurate for the dynamics actually happening in the model during hard computations.
That's huge. It means the very mechanism designed to make deep recursion trainable efficiently was based on a false premise in their actual usage. The HRM was essentially training with noisy, incorrect gradients for its recursive steps.
Exactly. It was likely relying mostly on the standard backprop through the final output head, and the recursive part was learning very poorly due to the flawed gradient signal from the IFT approximation. That probably explains why its performance hit a ceiling.
Okay, so the mathematical foundation was cracked. What else?
ACT efficiency. The way they implemented ACT using Q-learning was inefficient. It needed 2 full, expensive forward passes through the network for every single optimization step. One pass to get the prediction and another pass just to calculate the target value for the Q-learning loss.
Doubling the training cost per step? Ouch.
Yeah, it slowed things down considerably. And finally, just biological justification and complexity. Using 2 separate features, ZHAAs, and 2 distinct networks, 5L or DEF-HAN, felt complex. It leaned heavily on these analogies to brain hierarchy, which are interesting, but maybe not computationally necessary. Was it the simplest way?
Which brings us to TRM, the simplification. Getting more by doing less. How did they ditch that complex hierarchy?
TRM basically threw out the explicit biological mapping. They reinterpreted the latent features. Instead of values and features, they just said, let your be the proposed solution, kind of like HRM's, the abstract output, and let ZL be the internal latent reasoning feature, more like HRM's, the scratch pad or execution trace.
So just 2 features again, but with a simpler interpretation.
Simpler interpretation. And they actually did ablation studies confirming that having exactly 2 features worked better than just 1 or trying to add more. 2 seemed to be the sweet spot.
And the networks? HRM had 2 4-layer networks.
TRM slashed that down. They replaced both of HRM networks with a single shared 2-layer network.
Whoa. From 8 layers of parameters, 4 and 5 numbers down to just 2 layers total. That's a massive cut in static parameters.
It's radical.
Yeah.
And the single network handles both tasks, updating the latent reasoning dealers and updating the solution here. The only difference is what inputs you feed it. When updating 7, you include the problem input $6. When updating gavant, maybe you don't, or it's only there implicitly through 7.
And why only 2 layers? That seems counterintuitive to deep learning dogma.
It does. But here's the fascinating insight. They found decreasing the number of layers to just 2, while simultaneously increasing the recursion depth, how many times you loop through that 2-layer network, gave the best generalization.
Why would that be?
Think about the data sets. They were tiny, only about 1,000 examples per task. A deep network with many layers has huge capacity, making it very prone to just memorizing those few examples overfitting. By making the network itself shallow, only 2 layers, minimizing static memorization capacity, but letting it run for many time steps, maximizing dynamic computation or execution capacity, TRM forced itself to learn general procedures rather than memorizing solutions. Less overfitting, better generalization on sparse data.
That's a really clever trade-off for these kinds of reasoning tasks. Minimize static parameters, maximize temporal computation.
Yeah.
Okay, but the absolute killer change in TRM must have been ditching that flawed IFT gradient, right? They abandoned the on-runner memory dream.
They did. They faced reality. The one-step approximation wasn't working reliably. So TRM went back to using full backpropagation through the recursion.
Ooh, didn't that bring back the o3-mini memory problem they tried so hard to avoid?
Yes and no. They managed it intelligently. Instead of approximating the gradient, TRM defines a full recursive process. For example, one awareness latent updates followed by one output update forms one recursion segment. Let's say they run this for $2 segment. During the first $T segments, they run the full forward pass to get the state. But crucially, they detach the gradients. No gradient computation or storage happens during those initial passes.
Ah, like in deep supervision, but without the intermediate loss.
Sort of.
Yeah.
Then, only on the final segment tollers, they do the forward pass and perform full backpropagation through all $1 plus $1 steps within that last segment.
So they accept the memory cost of DPTT but only for one segment's worth of computation depth at a time.
Exactly. They pay the memory price for the final $1 plus $1 steps, but not for the entire history times n plus $1. It's a compromise. More memory than the flawed all-allo IFT approach, but much less than full BPTT over the entire sequence. And critically, it provides a correct, robust gradient signal for the actual computation being performed.
And the million-dollar question, did this return to robust gradients, actually work?
Oh, did it ever? The results were night and day. Just this change alone, moving from the flawed one-step IFT gradient to full BPTT on the final segment, caused Sudoku accuracy to skyrocket. HRM's best was around 56.5%. TRM, with this fix, hit 87.4%.
Wow. That's definitive proof. The correct gradient signal is absolutely essential, far more important than the theoretical over-memory saving.
Completely validated the decision to accept the slightly higher memory cost for mathematical soundness.
Okay, so the gradient was fixed. What about the other improvements? They streamlined ACT too, right? Got rid of that inefficient two-pass Q learning?
They did. The original ACT was clunky. TRM simplified it dramatically. They threw out the second forward pass entirely. They also got rid of the complex continue loss target calculation.
So how does it decide when to halt now?
Much simpler. Just a binary cross-entropy loss on the Q-head's output, based directly on whether the model's current prediction is actually correct or not. If it's correct, nudge towards halting. If not, nudge towards continuing.
And did this simplification hurt performance?
Barely at all. The paper shows results like 86.1% accuracy with a simple ACT versus 87.4% with no ACT. It maintained almost all the performance while making training much faster and simpler. A big win for practicality.
They also added other stabilization techniques, didn't they? Like EA?
Yes, exponential moving average, EMA, on the weights, with a high decay factor like a 0.999. This is pretty common in domains working with small or noisy datasets.
Why was it needed here?
Because the datasets were so small and the tasks so hard, the training could be very unstable. The model could easily overfit or just diverge catastrophically. EM smooths out the weight updates, acting like a temporal ensemble, making the learning process more stable and robust, preventing it from chasing noise in the sparse data.
Makes sense. And the core architecture itself, the attention mechanism within that two-layer network, they even tweak that depending on the task.
Yeah, that was another interesting finding. For tasks with very structured fixed-size inputs like the 9x9 non-Sudoku grid, they found they could actually remove self-attention entirely. They tested a version, TRM MLP, using an MLP mixer-style architecture, just MLPs applied across positions and across features.
And it worked better.
Surprisingly, yes. For Sudoku, the attention-free TRM MLP got that 87.4% score, while the version with standard self-attention, TRM AT, only got 74.7%, over 10% difference. Suggests attention might have been unnecessary complexity, maybe even harmful for that specific task structure.
But attention was needed elsewhere.
Definitely. For the larger grid tasks like Mazehard or ARC-AGI, which use 30 times 32 grids and likely required understanding non-local spatial relationships, the standard self-attention in TRM-AT was essential. The MLP mixer version likely couldn't handle those long-range dependencies. So task dictates architecture details.
Right. Finally, let's nail down the hyperparameters that gave TRM its impressive computational depth. How deep did they push the recursion?
They optimized it and landed on 2 pretty high-level updates, and within each update, one N60-60-60 latent update steps before the output update.
So 2 3 in a 666. That's opthi 6 latent steps plus 1 output step times 3 segments, roughly 21 steps per segment times 3.
Wait, how do they count the depth? Is it 2 times n plus $1?
The paper mentions 42 recursions of effective depth, I believe. The exact calculation might be subtle, maybe up plus 1 times t total steps. Or perhaps on times t latent steps plus $2 output steps. Let's say the key number is around 42 effective computational steps generated by iterating through that two-layer network.
Okay, 42 steps. That's significantly more than HRM's setup, which was $2 and 2, maybe around 6 or 8 steps per segment.
HRM's 2 and 2 is maybe only 24 recursions total in the configuration they used for the hard tasks. TRM deliberately increased the computational budget, the number of recursive steps, finding that 42 was optimal for these problems.
And the other basics: optimizer, batch size, standard stuff mostly. Atom W optimizer, small learning rate warmup, which is typical, a reasonably large batch size of 768, and a hidden dimension of 512 for the two-layer network. Pretty standard training setup, just applied to this recursive architecture. The magic wasn't in exotic optimizers, it was the recursive structure and the correct gradient.
All right, let's get to the payoff, the performance comparisons. This is where TRM really shines, especially against the LLM giants. We need to stress again, though, the training conditions.
Absolutely critical. These models, HRM and TRM, were trained on only about 1,000 input-output examples per task. No massive pre-training on internet text, no special chain of thought labels showing the intermediate steps. Just the problem and the answer.
So this is testing raw algorithmic generalization from very little data.
Exactly. And the benchmarks themselves were chosen to be hard, specifically designed to break models that rely on shallow pattern matching.
Tell us about them. Sudoku Extreme.
Yeah, not your standard newspaper Sudoku. These puzzles require, on average, 22 backtracking steps for a good algorithmic solver. That demands serious iterative search and constraint propagation, much harder than typical AI Sudoku benchmarks.
And Maze Hard.
Finding the optimal path in large, 30 times $30 grids. The hard part means the shortest path length is deliberately very long, often over 110 steps. Again, requires sustained, long-range planning, not just local heuristics.
Okay, classic algorithmic challenges. And then ARC-AGI, the one often seen as a proxy for more general intelligence.
Right, the abstraction and reasoning corpus. ARC tests inductive reasoning. You see a few input-output grid examples demonstrating a rule or transformation, and you have to infer the underlying rule and apply it to a new input grid.
So it's about generalization to totally new tasks based on minimal examples.
Exactly. And ARC-AGI2, which they also tested on, supposedly emphasizes deeper compositional reasoning rules built on top of other rules. It's meant to be a real challenge for current systems. Okay, the stage is set, hard problems, minimal training data. How did the big guns, the massive LLMs like Deepseek R1, 671B parameters, or Claude 3.7, presumably huge, fare on the algorithmic tasks?
This is where the narrative completely flips. On Sudoku Extreme and Maze Hard, they scored 0.0%. Flat zero.
Zero, despite all their parameters and pre-training.
Zero. They simply cannot execute the long, precise, step-by-step reasoning required. Their fixed depth architecture, their inherent AC dollars or TC dollar limitations, structurally prevent them from solving these problems end-to-end without some external scaffolding like QT, which wasn't allowed here.
Wow. Okay, contrast that with TRM.
TRM's victory is stark. On Sudoku Extreme, the tiny TRM MLP, the attention-free one, maybe around 5.7M parameters, achieved 87.4% accuracy.
From 0% for giants to nearly 90% for a tiny recursive model. That's stunning.
It really highlights the architectural difference. For Maze Hard, which needed attention, the slightly larger TRM model hit 85.3%, again, demonstrating robust long-range planning capability where the LLMs failed completely. Okay, algorithmic tasks show a clear win for recursion. What about the more general reasoning task, ARC-AGI? How did TRM do there compared to, say, code methods or those big LLMs?
This is maybe the most significant result for the AGI conversation. On IRC-AGI1, TRM scored 44.6%.
How good is that?
It's significantly better than the competition reported in the paper. The best comparable co-approaches on ARC were apparently scoring in the mid-30s percentile range. And remember, Deepseek R1, the 671 billion parameter model, it scored only 15.8% on the same ARC-AGI1 benchmark.
So TRM is nearly 3 times better than a model over 10,000 times its size on a task designed to measure general reasoning and abstraction.
Yes. The ability to compute deeply and iteratively, controlled by the recursion, seems to unlock a form of inductive reasoning that sheer scale and externalized code just can't replicate effectively, at least not on these challenging low-data tasks.
This really underscores the point about computational universality, doesn't it? That recursion lifts these models beyond the fixed depth limits.
Absolutely. Architectures like universal transformers and now HRM and TRM are theoretically Turing-complete, given enough time and memory. They aren't bound by the fixed number of layers like standard transformers. They can, in principle, simulate any algorithm by dynamically allocating computational steps over time via recursion.
They overcome the ACC-TC$-EPR barrier.
Exactly. They trace static depth for temporal depth, and that seems to be the key for unlocking true algorithmic power.
Did they look inside the model, visualizations of how it uses this temporal depth?
They did provide some insights based on analyzing the hidden state dynamics during problem solving. And it suggests the models learn adaptive strategies.
Like what?
For the maze task, the activity patterns apparently looked like the model was exploring multiple paths simultaneously and then pruning them almost like a parallel search. For Sudoku, the dynamics more closely resembled a depth-first search, including evidence of internal backtracking, where the model seems to reverse its state trajectory when it hits a constraint violation.
So it's not just blindly iterating, it's directing the computation in structured ways.
Seems so. And for ARC-AGI, the process looked more like optimization or hill climbing, iteratively modifying the grid based on the inferred rule until it converges on the likely answer. It shows the model flexibly uses its fixed computational budget, those 42 steps, in different ways depending on the task structure.
Very cool. Now let's connect back to that biological inspiration you mentioned for HRM. There was an emergent property they found, right? Something about dimensionality.
Yes, this was a fascinating secondary finding from the HRM paper analyzing the trained model. They used a measure called the participation ratio, or PR.
What does PR measure?
It's a way to estimate the effective dimensionality of a neural representation. If PR is high, it means the information is spread out across many dimensions of the hidden state vector. The representation is rich and distributed. If PR is low, the information is concentrated in just a few dimensions.
Okay, so they measured the PR for the high level and low level states in the trained HRM.
They did. And the results were striking. The high-level module, 7 days dollars, which was supposed to handle abstract strategy, ended up operating in a very high-dimensional space. Its PR was measured at 89.95.
Wow, nearly 90 effective dimensions. And the low level...
This amount of dollars, responsible for the detail execution, operated in a much lower dimensional space. Its PR was only 30.22.
So clear separation. High dimension for abstract planning, low dimension for concrete execution.
Exactly. And the ratio between them, high PR, low PR, was about 89.95, 30.22, which is roughly 2.98.
And why is that number interesting?
Because neuroscience studies measuring the same PR ratio across hierarchical areas in the mouse cortex found a very similar value, around 2.25. Higher-order, more abstract cortical areas also seem to use higher dimensional representations than lower-level sensory or motor areas.
That's an uncanny parallel. Did the model have this hierarchy from the start?
No, that's the crucial point. They checked the PR and the untrained, randomly initialized HRM, and there both $7 and stallers had low and similar PR values, around 40.
So the network wasn't built with this dimensionality difference, it learned it.
It learned it. This high-dimensional abstract layer guiding a lower-dimensional execution layer seems to be an emergent organizational principle that the network discovered autonomously during training because it was effective for solving the reasoning tasks.
That implies this kind of structural organization, high dimensionality for flexibility, low dimensionality for constrained execution might be fundamental for robust reasoning, whether biological or artificial.
It strongly suggests that, yes.
Okay.
And it hints that standard feed-forward deep networks, which sometimes suffer from representational collapse into lower dimensions, might be missing this crucial organizational structure that recurrence seems to naturally foster.
The ability to dynamically organize the computational space seems key. #tag outro. Okay, let's try to wrap this up. We've gone deep into HRM and especially TRM. What's the single biggest takeaway from all this for AI researchers?
I think the core insight is pretty clear. The kind of computational depth needed for complex algorithmic reasoning doesn't necessarily come from having trillions of parameters in a fixed-depth architecture.
Right.
It can be achieved much more efficiently through temporal organization using controlled recursion, like in TRM, coupled with robust training methods, like full backprop on the final loop and deep supervision concepts.
So it's a direct challenge to the dominant scaling paradigm. Maybe we're over-engineering for size and under-engineering for, well, computational structure and dynamics.
It certainly looks that way for these kinds of reasoning tasks. The results suggest the bottleneck isn't the raw number of parameters, but the shallow computational path imposed by fixed-depth architectures. TRM shows a different path forward.
And if we connect this back to the goal of AGI, TRM's success seems to hinge on its ability to structure its internal computation over time, right? Iteratively refining, backtracking internally, allocating its thinking time effectively.
Exactly. That temporal unfolding is what allows it to break free from the complexity class limitations, ACCC dollar, that plague standard transformers on these tasks. It unlocks genuine algorithmic capability.
And that finding about the emergent dimensionality hierarchy, a tiny model spontaneously learning an organizational principle seen in the brain. What does that tell us?
It's incredibly suggestive. It implies that maybe the right kinds of structure, particularly those involving recurrence and temporal dynamics, are inherently better suited to discovering the organizational principles needed for flexible, robust intelligence. Maybe the structure itself guides the learning process towards solutions that mirror biology because those solutions are computationally efficient.
So what's the next step? Where does this research direction lead?
Well, the big challenge now is scaling these principles: efficient recursion, latent reasoning, maybe dynamic depth, Beyond these specific supervised reasoning tasks, can we build, say, a large foundation model that incorporates this kind of iterative internal computation for more open-ended tasks like language generation or multimodal reasoning?
Combining the fluency and world knowledge of LLMs with the rigorous reasoning engine of something like TRM.
That's the dream, isn't it? Fusing the strengths of both approaches. That seems like the next frontier. How to integrate efficient, deep, latent computation into the broader generative AI landscape.
Okay, so that leaves you, our listener, with a final thought to chew on. The big breakthrough here, TRM, came not from adding more complexity or layers, but from radical simplification down to just 2 layers, and by rejecting complex, flawed mathematical approximations like IFT in favor of robust, fundamental gradient propagation through the recursive loop.
Less was truly more computationally.
So the provocative question is this. Is the real path towards more general artificial intelligence found not in maximizing parameters or intricate designs, but in the relentless pursuit of elegant simplicity, structural efficiency, and the mastery of controlled temporal computation?